Today's Bay Area innovator is Capella Kerst, the CEO and founder of Gecko Materials, a bio-inspired adhesive company.
So when you place it down and you pick it up, you have a little bit of shear contact on both sides,
Right.
then it falls off under its own weight.
She invented the groundbreaking mass manufacturing process of the Gecko adhesive, a revolutionary product that requires no force to detach.
I took the bottle of wine with Gecko Materials and I held it up at a VC party, and a lot of people were like, okay, can I invest? Can I wire you money today?
Capella started the company in her garage in 2021 after getting her PhD in mechanical engineering from Stanford University, as well as other degrees from UC Berkeley and UCLA.
If you're passionate and you're solving a real pain point and problem for a customer, go for it.
This is Bay Area Innovators, and I'm your host, Steve Ispas. Capella, welcome to our program.
Thank you so much for having me. It is very much an honor to be here on the show with you.
Thank you, thank you. Well, so we want to talk about your company. You started this company, you were at Stanford, you did your PhD there, and then you came up with the Gecko Materials company. And I kind of want to ask you, it seems like the norm now that startups start in a garage, and Stanford becomes such an ecosystem for these companies to create. Tell us how you get started and how much of a role did Stanford play into enabling this to happen?
Yes, so Gecko Materials was spun out of my PhD, so it played actually a huge role. I did my PhD for over 5 years at Stanford, and then I actually did take it to my mom's garage to start the company the day after I put in my thesis defense and paperwork, and everything was signed off and done.
So you started a company a day after you finished your PhD, pretty much?
Yes,
Okay.
yes. I had known for the last year and a half of my PhD that I wanted to start Gecko Materials as a company, and so I kind of, did some work on the side, and then my advisor was like, okay, you can stop doing those tests because you're not a company yet, but that's good enough for a paper. And so I went through the process of doing that, in which I wrapped up more research and then prepped the company and had it ready and able to hit the ground as soon as I was no longer a PhD student.
Please tell us a bit about your invention, what your company does. And to be honest with you, I really like the fact how simple the product is. Sometimes we have these very complicated things that it's hard to explain, but please tell us, what your company does, what your product is.
Yes, so Gecko Materials is the next industrial Velcro at the very basic form. It's a one-sided material that has micro hairs that are pulled and sheared to create an extremely strong force, namely the van der Waals force. So it's an attraction between two surfaces, and our Gecko Materials can hold on to smooth and micro-smooth surfaces. 1-inch tile can support 15 pounds vertically. 6 1-inch tiles can pull a car, and I know we have this bottle of wine that I'll do later that I can hold by pinky. You can reuse it over 120,000 times. For reference, Velcro can only be used 2,000 times, so it's a more sustainable mechanism in which to attach and detach over the long period of time. For pick-and-place robots, there's no residue left behind, there's no marring surface. You can use it in any barometric environment, so like atmospheric pressure like the room we're in, hydrogen, nitrogen, and a vacuum chamber. Because you can use it in vacuum, you can use it in space. We're on the International Space Station. Actually, later today, it's super exciting, one of our customers is launching into space with Gecko Materials on their robot.
That's fantastic.
Yeah.
So one of your customers is the International Space Station.
Yes.
Wow.
Yeah. And then another space company is launching a device that has kind of arm tentacles, and it has Gecko Materials, and it's using for grasping and attaching. So we're super excited for them.
Please tell us more about your existing customers. Who are they and how they are using the product?
Yes, so we have our initial go-to-market strategy, though we are the next industrial Velcro, is threefold. It's pick-and-place robots, drones, and space. For pick-and-place, we focus on automotive and semiconductors, drones, public and private, space, public and private. So in the sector of the automotive, we have Honda, Ford, Toyota, Hyundai, GM. Yeah, GM is an amazing company. Just visited them in Detroit. And then we have semiconductor companies. So we work with the top semiconductor manufacturers. So they manufacture equipment for TSMC, Samsung, Intel, and other semiconductor companies. So we're helping them save energy, time, and money with these new inventions of how to do wafer handling and transferring in a more energy efficient manner. We replace suction, airline, and vacuum dependencies on pick-and-place robots. For the space industry, as I mentioned, International Space Station, and every space company. Like, there is no comparison for an adhesion you can use in space and reuse. So ISAM, OSAM, those are in-space servicing, assembly, manufacturing, and on-orbit servicing, assembly, manufacturing.
So for the semiconductor companies, how is it used? Is it mainly the robots that pick up the different devices, like very, very small devices?
Yes, so you can actually rate it to the largest and heaviest object, and anything smaller and lighter you can pick up using that same end effector. And so for the wafers, you can do whole wafers, you can do dice pieces and parts. You can also do sensor mounting within the semiconductor industry. So there's about 8 different engineering teams that we're working with at one company alone. And then, yeah, with Samsung, I'm actually going to Samsung later today and meeting with some other engineers there. And so there's various, pain points and problems that we're help solving while saving energy, time, and money.
So what is it replacing for the handling of the wafers? Because it's not Velcro, right? Or
yeah, no.
Yeah, I couldn't use Velcro for that.
No, because Velcro is 2 sides. So suction, airline, or vacuum dependency. So you have like chucks, or you're replacing kind of manual things that are very tricky to manipulate. So they require large amounts of, pump down times and outgassing times. So you vent a chamber and then you pull it on a chamber once you've manipulated it again. And that's a whole cycle that you're wasting energy for when you could just use a robot arm and manipulate it in-house or in vacuum alone with that part. So you can do a deposition on one side of the glass and then manipulate it and do a different deposition on the other side without venting the chamber and pulling vacuum again.
That makes more sense now when you talk about saving energy, how that actually works out.
Right.
And now this whole invention is from nature, right?
Yes.
It's from the feet of a gecko. So how did that come about?
Yes, so over 20 years ago, Mark Kokoski kind of answered a DARPA call. So it was when biomimicry was started between a Berkeley and Stanford collaboration. So my PhD advisor is an amazing man, and he was, one of the inventors of the biomimicry space. And so they studied the gecko and how it climbed up smooth vertical surfaces, and it's not excretion, it's not suction, and it's not little micro like hooks. They're actually these little hairs that when pulled in shear create an extremely strong force.
The van der Waals.
Van der Waals, exactly.
Which you'll need to study separately. That's a bit of a different topic and not as simple, but we'll look into it.
Yes.
If our audience wants to look into it.
A whole PhD on that, so I, barely grasp it. No, it's a great phenomenon.
Yeah.
But with the study of biomimicry, Berkeley looked at the actual gecko, and then Stanford made it man-made. So it went through 4 generations till the one that you see now. So I came in the lab after like 15 years of R&D research. I was put on the project to do the next generation microstructures, so fine-tuning, kind of analyzing it in, COMSOL and such like that, so numerical analysis and computer kind of replication of how much force you're going to get with those hairs when pulled in shear. And then I helped invent the mass production metal molds and techniques, as well as improving the material structure itself. So the geometry I assisted in, and that's how I got my start into it. And then I invented the mass production and then the some proprietary black boxing pieces as well.
So it's man-made, right? It's not the actual feet of the, no, okay.
I know,
but
people are like, are you harvesting geckos? I'm like, no, we're not animal cruelty. PETA's not coming after us.
But it basically you learn from the technique of the gecko.
Yes, looked at God's great creature, the gecko, and how could we, improve on it and innovate on it. So, yeah.
Maybe show us a little bit how it works.
Yes. So this is a full bottle of wine. This is my famous demo. I'm just going to pick it up, and then you turn it over, and it falls off under its own weight. Do you want to give it a try? So basically you have...
Oh, I don't want to mess it up, but sure.
No. So you're just going to take it, and you just plop it down like that, and then just pick it up with your pinky, and then turn it. There you go. And then turn over, and it falls off so quickly.
That's
and I know there's
amazing.
some other objects you want to try.
Yeah, please.
So let's try an apple.
So these are some small hairs on it. That's what it is.
Yeah, it's super thin. They're opposed in different directions. So one side is facing one way, the other side's facing the other way. So then when you place it down and you pick it up, you have a little bit of shear contact on both sides.
Right.
Then it falls off under its own weight. And I love a good persimmon. I did a rotten tomato on stage, and then it falls off. Oops. Sorry.
That's pretty awesome. It's such a simple invention, and it's so useful.